Hello, this is a video about transition interface sampling, TIS. And in this video, I give more explanation about an example of this methodology, the maze. We call this a maze because we have a molecule in state A, and this molecule needs to permeate all the way to the other side of this maze towards state B. In this video, the maze is not so complicated. There are some very hard walls, so they have an infinitely high potential energy, so the molecule cannot jump out of it. And then we have a hole here, and this hole forms an entropic barrier. On the other hand, the molecule could also permeate through this channel, and this is a simple wall. It's a low energetic barrier over which the molecule could hop in order to reach the state B. So we have two permeation channels, and the molecule has to find its way to permeate to the other side. Now, to represent this in a simulation, we created this maze potential with a smooth potential, not with hard walls, and we let a Langevin particle move through this maze. Again, here we have on the left side state A. State A represents the water phase. So the molecule is in the water phase, and then the molecule has to permeate through the membrane, the maze part, and then reach the other side, the state B. We have represented the hard walls by a potential energy barrier. You see here it's quite high, 200, and here we have a passage which has a very low free energy, but still it is very narrow, and so that's an entropic barrier. On the other hand, we have here a quite low wall, and the molecule is able to hop over this barrier. The units in this graph are all reduced units, as you can read on the retis.org website. For instance, z, of course, is a distance, and y is also the distance. We call z the permeation coordinate, and y is here a collection of orthogonal degrees of freedom. This number 5 means then that it has an energy unit. Now, if we run a simulation with a particle on this two-dimensional surface, then it represents a molecule permeating through a membrane. We now look at the results of that kind of simulation. Here we have different ensembles. We start with the 0 minus ensemble, and the 0 minus ensemble is sampling state A. State A lies to the left of lambda 0. Now here we have the lambda 0 interface, and in 0 plus we have the positive side of lambda 0. And these are these blue paths here. You see that in 0 plus there's not that many paths that are reaching state B. In fact, there are none. Now that changes if we look at the other ensembles. In ensemble 1 plus, we do have a few reactive paths, the green ones. In 2 plus, that's also the case. 3 plus, 4 plus, we even have many more reactive paths. And you can see that the paths, the reactive paths, they can be going over the energetic barrier, or they can be going through the entropic barrier. I want to say something more about the legend of these graphs. We have LML, MLR, RML, RMR, LML, MLR. We have those labels in the graphs in the legend. Now, this is a shorthand notation for left, middle, and right, because every interface has three interfaces, every ensemble has three interfaces that are connected to this ensemble. The left is a start of the path, the M is the crossing condition, and R is then the right interface of that ensemble. Because we sample transitions from A to B, the left and the right interface are always lambda 0 and lambda B. But the middle interface changes with the ensemble that you look at. In the 3 plus ensemble, the middle interface is lambda 3. Now let's look at the 0 plus ensemble. We have here those two labels. We see here that the left is lambda 0 and the right is lambda B. Now the middle interface is lambda 0 again. Now an LML L path means that you start at lambda 0 and that you go back to lambda 0. So it's doing a return. This is here an example of such a path. Now, an LMR path will go all the way to the right-hand side, so it will reach state B. It is a reactive path. And then if we look at all the paths that are sampled in the 0 plus ensemble, for instance, in this case, about 100,000 paths that we sampled, then the total number will be 100,000, and we will have this total number to be the sum of all the returning paths and all the reactive paths. On the graphs, we put them in percentages. If we now look here at the 0 plus, we see that we have a very small number, very small percentage of paths that are reactive and that reach the other side. In the 0 minus, we have a few more paths in this very specific case because some of the paths might reach the lambda minus 1 interface. Now, if we look again at our graphs with all the paths, then we see now that the green paths are the reactive paths and the blue paths are non-reactive, LML. Here in this low ensembles, we don't have many paths that are reactive. Here we have 10 randomly selected paths out of those 100,000 paths. None is reactive. Here we have more reactive paths. Here it's already 1. Here we have like 1, 2, 3. Here it's more difficult to count. 1, 2, 3, 4, 5, maybe 6. And here we have actually 1, 2, 3, 4, 5, 6, 7, 8-ish. We have many more paths. We see here a percentage of about 74% of reactive paths compared to the 0 minus to less than a percent of green paths. From this example, we can understand that by using transition interface sampling, we can generate ensembles, and in the high ensembles, we will have a very high likelihood to be reactive. And this allows us to actually see those reactive paths and get some statistics on them.